This is Euclid Book 10, proposition number 16. And this one's going to include a lemma. There's the diagram. Okay. If two incommensurable magnitudes be added together, the whole will also be incommensurable with each of them. And if the whole be incommensurable with one of them, the original magnitudes will also be incommensurable. For let the two incommensurable magnitudes AB and BC be added together. Okay, well if you add AB and BC together, you're going to get AC. AB plus BC gives you AC. I say that the whole AC will be incommensurable with each of the magnitudes AB and BC. Okay? So, all of AC is incommensurable with AB and BC. For if AC and AB are not incommensurable, some magnitude will measure them. Let it measure them if possible, and let it be D. So now we're going to say that, hypothetically speaking, D somehow measures AC and AB. Okay? Now we're going to say this line measures AC and AB. Do we see a problem coming up right off the bat? I bet we do. Therefore, D will measure BC. Okay, now we're going to say that D here measures BC. Well, but we already said that D measures AB. Therefore, D measures AB and BC. Therefore, AB and BC are commensurable. But by the hypothesis, we just said that they're not commensurable. So they can't be both incommensurable and commensurable at the same time. Doesn't work that way. Therefore, no magnitude will measure AC and AB at the same time. You might find a magnitude that measures AB, you might find a magnitude that measures AC, but there's no magnitude that will measure both AB and AC. So, there is no number that will measure both this and all of this. Won't work. Okay. Therefore, AC and AB are incommensurable by Euclid Book 10, definition number 1. Similarly, we can prove that AC and CB are incommensurable. Therefore, AC is incommensurable with each of the magnitudes AB and BC. Okay. We can now prove that these two are incommensurable. Therefore, AC is incommensurable with both of these. Next, let AC be incommensurable with one of the magnitudes AB and BC. Okay, so we're going to say that the whole of AC is either incommensurable with AB or AC is incommensurable with BC. We're not sure which. First, let it be incommensurable with AB. So now we're going to say that AC is incommensurable with AB. Okay, so the whole length AC is now going to be incommensurable with AB. I say that AB and BC are also incommensurable, for if they were commensurable, some magnitude would measure them. Let it measure them and let it be D. So now we're going to say that D is somehow able to measure AB and BC. Since then, D measures AB and BC, now we're going to say that D measures both of these. Do you see a problem coming up? Therefore, it'll also measure the whole AC. Now we're saying that D, somehow, because it measures these two here, it's going to measure the whole thing. But it measures AB also. Therefore, D measures AC and AB. So now we're saying that D measures AC and it also measures AB. Therefore, AC and AB are commensurable. But they were also by hypothesis incommensurable, which is impossible. So in other words, we're now saying that AB and AC, the whole length AC and the length AB, they're commensurable, but we just said they weren't. They can't be both commensurable and incommensurable at the same time. It doesn't work that way. Therefore, no magnitude will measure AB and BC. Therefore, AB and BC are incommensurable by Euclid Book 10, definition number 1. Therefore, etc. Okay. But this thing has a lemma. Okay. And the lemma says as follows. If to any straight line there be applied a parallelogram deficient by a square figure, the applied parallelogram is equal to the rectangle contained by the segments of the straight line resulting from the application. For let there be applied to the straight line AB. Well, we start off with a straight line here called AB. That's all we have at the first of this lemma, okay? For let there be applied to the straight line AB the parallelogram AD. So now we're drawing a parallelogram. A, C, D, and whatever other letter you wanted to put up here. Okay? That's your parallelogram. And we're going to have it deficient by the square figure DB. So now we're going to say that DCB and whatever other letter you want to put up here, this is a square. So this is going to be a parallelogram deficient by a square. Okay. I say that AD is equal to the rectangle contained by AC and CB. Well, we're now going to say the rectangle AD, okay, or parallelogram AD is equal to the rectangle formed by AC and CB. So what we would do is we would have a rectangle Okay, so if we took the length of AC and put it down twice, and we took the length of CB and put it down twice, it'd form a rectangle. And we're saying that the size of this rectangle is going to be exactly the same as the size of this one. Okay, now how do we prove that? This is indeed at once manifest, for since DB is a square, okay, DC is equal to CB. Now we're going to say that this line right here is going to be the same length as this one right here. And we can do that because it's a square. Okay. And AD is the rectangle AC and CD. Okay. So this is the rectangle AC and CD. And since CD is equal in length to CB, we can then say that this rectangle is going to be equal to this rectangle. And AD is the rectangle ACCD, that is the rectangle ACCB, therefore. And that is the end of that particular proof. Alright. I will tell you more in a future video. Stay tuned.